Hey everybody, Dr. A here, and in this video we're going to be exploring an example of frame internal loading. So let's go ahead and jump into it. In the given information, we're being asked to compute the internal loads at point C. So in this frame, we have two members. We have a member AB that's rigidly connected. That's what this kind of darkened corner connection represents. That's a rigid solid connection. And that's rigidly connected to a member BD, okay? Now, on AB, we have a uniform load of 0.2 KLF, and in the middle of BD, we have a 3-kip point load right in the midspan of it, okay? AB is 20 feet long, and then BD is 16 feet long in total. Now, the point that we're interested in is point C, which is 6 feet away from this corner at B. So let's go ahead and dive into the solution. So under the solution, we already have that we're going to use method of sections to pass a cut through point C. And then we're going to apply equilibrium equations to either of the free body diagrams. Now, we also make note we must solve for at least some external reactions before using method of sections. Why must we solve for some of the externals at least before using method of sections? Well, when we do method of sections and we put this cut through C, if we look at a left free body diagram, well, AY is going to show up there. Or if we look at a right free body diagram, dy and dx are both going to show up there. So no matter which side of the cut we analyze, we're going to need at least some of the external reactions. Now, again, we only have to analyze one side of the cut, not both. But for the purposes of this example and just to illustrate, you get the same thing in either case. I'm going to show work for both. I'm going to show us how we can get the solution using a left free body or a right free body diagram. And it won't really matter. You'll get the same answer. Now, one of them, my guess, will be a little bit easier to deal with than the other, but we'll find out, okay? So let's go ahead and let's say that we're going to draw a free body diagram of entire system. And the reason why we're going to start with this is so we can get those externals, okay? So here is my frame, and here is AY, and then over here we had a DY and a DX. We've got 3 kips right here in the middle. We have this rigid joint at B, and then we have this uniform load spread out over this vertical member, and this was 0.2 KLF. This vertical member was 20 feet, and then we had 8 feet lengths on either side of that 3-kip load, okay? So to solve for these externals, I'm just going to use basic equilibrium. I'm going to say sum of the moments about D equals 0. And I can solve for AY directly. I'm going to say negative AY times 16 feet. And then I'm going to say plus 0.2 KLF times 20 feet times 10 feet. And then we're also going to have plus 3 kips times 8 feet equals 0. I'm going to do some rearranging here, and I'm going to solve for AY, 0.2 times 20 times 10, and then combine that with 3 times 8, move it to the other side of the equation, divide by 16. And so I get AY is 4 kips reacting upwards. Now if I say sum of the forces in the y direction equals 0, hopefully you can obviously see what this should be. We should get dy is 1 kip, and that's going to be reacting downward. Now you can show your work on that and prove that, but dy is going to be 1 kip reacting downward, and then I can say sum of the forces in the x direction equals 0, and here I'm going to have 0.2 KLF times 20 feet plus dx equals 0, and I'll do some rearranging, and I'll get dx is 4 kips reacting to the left. Okay, so these are my external support reactions. That's great. All right. Now what we need to do is use method of sections. Okay, so I'm gonna turn the page, and I'm gonna say now we're gonna say use MOS and a left free body diagram. So this will be one option. Okay, we're gonna start by just looking at a left free body. All right, so the left free body diagram, we're going to have that vertical member. And, you know, we had this AY right here that was 4 kips reacting upwards. And we have the uniform load here. .2 KLF. And, you know, we turn the corner here. And we're making a cut somewhere. Where are we making this cut? Well, we made this cut at a distance of 6 feet away from point B. So right here, that's that 6-foot dimension. And remember, you know, that vertical member is still 20 feet tall, okay? Now, what shows up when we make this cut? Well, we're going to have a VC, a shear force at C, a normal force at C, and a bending moment at C. And now we're going to use equilibrium equations on this left free body diagram to get these internal loads, okay? So doing that, I'm going to start with, how about I just start with some of the forces in the X direction equals 0. So I'll have 0.2 KLF times 20 feet plus NC equals 0. So NC is just going to be 4 kips, and that's going to be pointing to the left, or, you know, numerically that would show up as a negative when I rearrange this equation. Next, I'm going to say some of the forces in the Y direction equals 0. And here I'm going to say 4 kips pointing up minus VC equals 0. I do some rearranging, and VC is going to be a positive 4 kips. And that's going to be pointing downwards because, you know, I did the calculations and I got a positive number, which means that VC is pointing in the direction I assumed, okay? Which also makes sense. It's got to be pointing down to counteract the 4 kips pointing up over here. All right, and then finally, I'm going to say some of the moments about the cut equals 0. And when I write that out, I'm going to have a 0.2 KLF times 20 feet times 10 feet, and then I'm going to have minus 4 kips times 6 feet, and then I'm going to have a plus MC equals 0, okay? And I'm going to do some rearranging. And what should I get? Well, if I move things to the other side of the equation, I'll have 4 times 6 minus 0.2 times 20 times 10. And I get negative 16 kip feet. But all that negative means is that I have 16 kip feet rotating opposite of what I drew in my free body diagram. So I drew a counterclockwise MC. I got a negative value, so it's going clockwise. So here are my answers: NC, VC, and MC. Now, if I look at a right free body diagram, should I get those same magnitudes? Absolutely. Let's prove it, okay? So here I'm going to say use method of sections with a right free body diagram. So here, I think this one's going to be a little bit easier to deal with. So I have that just, you know, horizontal segment, and I have that DY. That DY is 1 kip going down, and DX was 4 kips pointing to the left. And then I've got the 3 kips applied load. I have this cut section here, and I've got some dimension lines. So this is that dimension line between the load and the cut section. So that's going to be 2 feet. And then this other dimension line over here is the 8 feet, okay? Does that make sense that this is 2 feet? Yeah. I mean, remember it was 6 feet away from the corner here. And so that total length from the corner to the load was 8 feet. So this has got to be 2 feet, even though it's not really drawn to scale. But that's what you're looking at, okay? Now here, I'm going to go ahead and say I've got a shear force VC, got a normal force NC, and then I have a bending moment MC, okay? And so one thing I want you to notice, I drew these internal loads in the opposite direction as I did in my other free body diagram. Notice VC is down, NC is in tension, MC is counterclockwise in the left free body. In the right free body, all these are the opposite sense, just to really emphasize equilibrium at that spot, okay? And so here we go. We're going to just one at a time say sum of the forces in the x direction equals 0. And so clearly, you know, NC should be 4 kips pointing to the right, which is really in tension. I'm sorry, in compression, not tension. We're assuming tension, right? We did the calculations and it's pointing to the right in compression. And then we're going to say sum of the forces in the y direction equals 0. And so here VC is clearly going to be 4 kips pointing upwards. And then we're going to say sum of the moments about the cut equals 0. And so we're going to say minus MC. And then we're going to say minus 3 kips times 2 feet, and then minus 1 kip times 10 feet equals 0. We'll do some rearranging. We'll get MC is negative 16 kip feet. But remember, that negative just means 16 kip feet rotating in the opposite direction of what I drew in this free body. So I drew clockwise, and then this is going to be going counterclockwise. So let's check and make sure these answers correspond with each other. Let's look at NC first. We had NC 4 kips pointing to the right in the right free body diagram. We have NC 4 kips pointing to the left in the left free body diagram. Makes sense. Same magnitude, opposite direction. VC in the right free body diagram is 4 kips pointing up. VC in the left free body diagram is 4 kips pointing down. Again, makes sense. And then while I'm still in this left free body diagram, MC is 16 kip feet going clockwise. Go to the right free body diagram, you get 16 feet going counterclockwise. So those are your answers. And remember, we could have analyzed either of these free bodies. You do not have to analyze both of them. I just did both of them to show that you'll get the same answer, same magnitude of the answers in either case, but opposite directions, which is totally fine, okay? So part of the moral of this example is we kind of discovered that this right free body diagram was a little bit easier to manage compared to the left free body diagram, okay? So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this.